In this video, I just want to do a review of some of the relationships between molecules. So if I give you two structures, be able to tell, are they the same? Are they different? Are they resonance structures? Are they isomers, stereoisomers versus constitutional? We've also added conformations to that list. So I just want to do kind of a quick review of all of those different types. And then I made a flow chart that we'll look at kind of trying to go through and determine the relationship between a set of molecules. So the first one we had were constitutional also called structural. They do have other names. Sorry about that. So constitutional, structural, isomers. And these are going to have the same molecular formula. But the atoms are going to be connected differently. So I'm going to have different connections between atoms. So essentially they're going to be connected in a different order. We could say different atoms connected to different atoms, right? It's the same total atoms, right? If I have two carbons in one, I have to have two carbons in the other. Otherwise, they don't have the same molecular formula, which is our first criteria here, but they're connected differently. So the atoms are connected in a different order. In the example, I have butane. Oop, I almost drew the same thing. Or we can look at 2-methylpropane, right? Both of them are C4H10 if you were to count the hydrogens or use your formula for saturation, right? CnH2n plus 2. So same molecular formula, but they're connected differently, right? In butane, I have a chain of 4 carbons. In my propane, I have a chain of 3 carbons, and then I have a methyl group on carbon 2. So the atoms are connected in a different order. So these would be structural or constitutional isomers. Again, there's a few other names. These are the two that I tend to use the most. We also had resonance structures. Remember, resonance structures don't actually exist, right? What exists is the hybrid. But we use resonance structures mostly out of convenience. It's just easier. The hybrids can be kind of complicated to draw, particularly if one of the resonance structures contributes more to that hybrid than the other, then it's very difficult to draw the hybrid. So while structures don't exist, we use them. So if I give you a set to be able to determine, are they resonance structures? So resonance structures are going to have the same molecular formula. The atoms are going to be connected in the same order. So we could say the same atoms are connected to the same atoms, right? I haven't changed any of my sigma bonds, right? The sigma bonds are the same. What's different is the electronic organization. Since my sigma bonds aren't changing, but yet my electrons are arranged differently, that means that anything that's not in a sigma bond can be arranged differently. So that leaves me pi electrons, right? Double and triple bonding electrons, and then also lone pairs. So my electronic organization, it's taking me forever to write that word because I keep spelling it wrong. Is different, right? We would say our pi bonding electrons and non-bonding or lone pair electrons are distributed differently. right? That's what we mean by that, right? The only way to have a different organization of my electrons but have my sigma bonds being the same is for pi bonding and lone pairs to be distributed differently. And you guys have seen lots of examples of resonance, but we will put one here just to be complete. Remember, I don't always include those lone pairs. I assume at this point in the semester that if I was to put a negative charge on that oxygen, that you would be able to draw in the 3 lone pairs. So the relationship between these two, do they have the same molecular formula? They do. They both have 4 carbons and 1 oxygen, and if you were to count the number of hydrogen, they're going to be the same. Are the atoms connected in the same order? I have a chain of 4 carbons, and then the second carbon from the right is bonded to an oxygen. So yes, my atoms are connected in the same order. Is my electronic organization different, right? Are my pi bonding electrons in lone pairs distributed differently? Yes. The molecule on the left, I have a pi bond, so I have 2 pi bonding electrons in 2 lone pairs. On the molecule on the right, I have no pi electrons and I have 3 lone pairs. So the relationship between these two, there are resonance structures. I do want to go back up and do one more example of constitutional isomers. Remember that it doesn't have to be the same functional group, right? The example I gave you were both alkanes, but we could actually have another example where I have different functional groups. So this alcohol and this ether, right? If I was to figure out the molecular formula for them, they both have 3 carbons, they both have 1 oxygen. If you were to count the number of hydrogens, they are going to be the same. 1, 2, 3, 4, 5, 6, 7, and this one makes 8. 1, 2, 3, 4, 5, 6, 7, 8. So they do have the same molecular formula. Are the atoms connected in a different order? Yes, right? In my alcohol, I have a chain of 3 carbons that's bonded to an oxygen, which is bonded to a hydrogen. In my ether, I have 2 carbons, which is bonded to an oxygen, and then that is bonded to a carbon. So my atoms are connected in a different order. So they don't always have to be the same functional group, right? We started out learning them with the same functional group, but they don't need to be. So as long as they have the same molecular formula, but the atoms are connected in a different order, constitutional. Resonance, same molecular formula again. The atoms are connected in the same order versus different order. So same order. Here we have different order. But my pi bonding electrons in lone pairs are distributed differently. We added conformations. And conformations, again, are going to have the same molecular formula. They are going to have the atoms connected in the same order. These guys are actually not different molecules. They're actually, you could almost think of them as identical, but just oriented differently. So same atoms, the atoms are connected in the same order. And one can be converted to the other by rotating a bond. And it doesn't, in the case of like chair conformations, right? We don't rotate the bond a full like 180 degrees. We're just rotating it a little bit, but it's still rotating a bond, right? We're not disconnecting an atom and reconnecting it someplace else, which is what we would have to do with our constitutional isomers, right? If I look at these two, if I want to make one into the other, and I'm going to make the first one into the second one, I would have to break this bond, take that atom, move it over to here, right? I would have to disconnect. I'd have to break a sigma bond and move them over. Resonance structure is the only thing I'm moving, again, are my pi bonding electrons in lone pairs, so the atoms are connected in the same order. My conformations, my atoms are also connected in the same order. My electronic organization is the same. How I'm going from one to the other is I'm rotating a bond. And then we also added stereoisomers. Stereoisomers have the same molecular formula. The atoms, again, are connected in the same order. So the same atoms are connected to the same atoms. The difference between these is the three-dimensional orientation in space. So the atoms or groups, it's not all of them, but usually like a couple, like the substituents. We could say that, substituents. It could be the entire molecule. We'll look at other types of stereoisomers in chapter 5, are oriented differently. In three-dimensional space. I cannot convert one into the other by rotating a bond. Cannot convert one into the other by rotating a bond. The only way to convert one into the other for these ones is to, again, detach an atom, move it in three-dimensional space. So if it was going back, and let's say I need to move it to the front, right? So I'm moving it in three-dimensional space to a different orientation, but then I'm reattaching it to the same atom, right? My molecules or my atoms are connected in the same order. With my structural isomers, I was removing it and moving it to a different atom because they're connected in different orders. Here I'm removing it, but I'm reattaching it to the same atom, but just oriented in space differently. So if I was to look at, right, remember we had cis-trans isomers this week, or last week, sorry. And the difference between those was the orientation of those groups. So in the one I drew on the left, right, both of those methyl groups are coming out at us. The molecule I drew on the right, the one on the top is going back. The one that's clockwise to it is coming out at us. So these have the same molecular formula. I have 6 carbons in the ring on both of them, and then an additional carbon in the 2 methyl groups, right? They're 1,2-dimethyl cyclohexane. So they both have 8 carbons. If you count the number of hydrogen, they're going to be the same. The atoms are connected in the same order, right? I have a ring of 6 for both, and I have a carbon group on adjacent carbons. If I was to name them, they're both 1,2-dimethyl cyclohexane. The difference between them is the orientation in three-dimensional space of those groups, right? So this one is the same on both, so I'm going to ignore that one because it hasn't changed. I'm going to look at the difference. This is coming out at us, or sorry, going back. This one is coming out at us. And if I wanted to make this second one into the first one, right, I would have to take this group, I would have to take it off, I would have to move it from the back to the front and then reattach it to the same atom. I can't rotate it and make it come forward. I can rotate it and put it in a chair conformation. Remember, conformations we can get by rotating bonds, but I can't actually have that group that's going back coming forward without detaching it and removing it. So these are going to be stereoisomers of each other. This was my cis isomer. This is my trans isomer. Again, in chapter 5, we're going to have other types of stereoisomers. Cis-trans are not our only type, but they're the ones that we know now. So kind of going back through these again. Constitutional isomers, same molecular formula, atoms are connected in a different order, right? Different atoms connected to different atoms. If you were to name them, they have different names. Resonance structures, same molecular formula, atoms connected in the same order. The only thing that's different are my pi bonding electrons and lone pairs. So my electrons are distributed differently while keeping my sigma bonds the same, right? We're not changing sigma bonds because my atoms are connected in the same order. Conformations, these are essentially the same molecule, right? Same molecular formula, atoms are connected in the same order, and I can get one into the other by just rotating a bond. If I was to name them, they're going to have the same name. Stereoisomers, same molecular formula, atoms connected in the same order again, but this time I cannot convert one into the other by rotating a bond. The only difference between the stereoisomers are going to be how they're oriented in space. So is one going out and the other's coming back? And then on the other molecule, are they both coming out or are they both going back? So oriented differently in space. Again, I cannot convert one by rotating a bond or flipping it over even. Be careful for that. We should add that. Over, etc. So just watch out for that. So cis-trans. By flipping over, I mean if I was to draw this one, these are identical. Those are not stereoisomers, right? I don't have to rotate a bond to get one into the other, so they're not conformations. I don't have to detach an atom to get one into the other. All I have to do is take the entire molecule and flip it over, right? Whether they're both coming out or both going back, it's the same thing, just upside down from each other. So be careful for that. So I did make a flow chart. I pre-made it. I'm just scrolling up to it here. I've never made a flowchart for this topic before, so watching me do it would be a really painful experience for both of us. So I pre-made it. So I'm just going to kind of hover here. You're probably going to want to hit pause because you want to copy it down. So I'm just going to hover here for a second. There's more. There's probably going to be 3 screens worth. So if you want to copy this, and then I'll scroll down to the next one. Okay, our next. So again, copy this down and then we'll scroll to the next one. Okay, that's a good spot to leave it. Again, you'll probably need to hit pause because I'm not going to leave it for that long. Okay, and then the last, this will be the end of it. Okay. Oftentimes when I make flowcharts, as I go through it, I find flaws. So I did a couple examples with this and it seems to be pretty sound. So hopefully that will hold true and we won't find mistakes with it as the semester goes on. But what I want to do is just go through some examples using the chart. So I'm going to give us a set of molecules. We're going to go through the chart and we're going to try to figure out what their relationship is. So our first one, and you might not even need the flowchart. Some of these are probably pretty obvious, and if you're good at it, then great. You won't need the chart. But if you're struggling, then this might be helpful. Okay, so our first set. Our very first question, where we're going to start with all of these, do they have the same molecular formula? So that's the first thing we want to check. So if I look at our example here, this one has 1, 2, 3, 4, 5, 6 carbons. This one has 1, 2, 3, 4, 5 carbons. So right away, no, our molecular formula is not the same. So these guys are just different. They're not isomers of any sort, right? They're not constitutional isomers. They're not stereoisomers. They're certainly not resonance structures. I don't even have pi bonds, right? Or lone pairs. They're not conformations, right? I can't rotate a bond and all of a sudden add an additional carbon. So these are just different. I did put neither in parentheses just because that's how I usually say it on exams or quizzes, right? You'll have like a little drop-down menu and you have to choose if they're constitutional isomers or so on, and then neither is usually a choice. So they're just different. They're none of these things. Let's look at this versus this. So again, we're trying to determine what's the relationship between these. Our first question, do they have the same molecular formula? They both have 4 carbons. They're both saturated, so they are going to have the same number of hydrogen. So they're both C4H8. So yes, do they have the same molecular formula? Next, we'll ask ourselves this question. Are the atoms connected in a different order, right? If I look at this, I have a chain of 4 carbons. Here I have a chain of 4 carbons. So are they connected in a different order? No, right? They're both chains of 4 carbons. So then our next question, is the electronic organization different, right? Are my pi electrons and lone pair electrons different? I don't even have that, so no. Right? This one wouldn't have resonance. If you're looking for a resonance source, I don't have one. So our next question, we're just following our chart. Can you convert one into the other by rotating a bond? So let's go back up and look at these. So, and it doesn't matter which one we look at. I'm going to look at the first one. If I was to rotate this bond between the 2 carbons, what's going to happen is this can flip around in the order that I'm rotating it. It would actually flip in the back and then come back out. So can I rotate that bond and make this carbon right here in that orientation? Yes, I can. So these, going back to our chart, can I convert one into the other by rotating a bond? Yes. So that makes these conformations of each other. Right? Before you learn that word, we just would have said they were identical, right? They're the same thing. They're both, if you were to name them, they're both butane. And that's how it is going to be for conformations. They're going to have the same name. It's just that if I was to put these into Newman projections, this one is going to be eclipsed. Can't spell. This one is going to be staggered, right? If you were to look down on the end, this bond is going to be eclipsing that bond. I'm just getting rid of all the highlighting here, so when we go through another example, we don't have things pre-answered or pre-pointed out. I think that's all of it. Okay, let's do another one. So another example for us. And again, you might not even need this flowchart. So again, going through, do I have the same molecular formula? Yes, right? I have 6 carbons, right? I have a ring of 6 in both. I have 2 bromines. Are they connected in a different order? No, right? I have a ring of 6 in both, and then adjacent carbons, I have bromine. Be careful, if I would have done a bromine here and a bromine here, now they are, right? If I wanted to compare the third one I did to either one of the original 2, they are connected in a different order, right? If I was to name them, they would be different. The first 2, 1,2-dibromocyclohexane. The third one I did, 1,3-dibromocyclohexane. So be careful. This third one would be a structural isomer of the top 2. So just be careful for that. When I say same order, those bromines are on adjacent carbons in one. They need to be on adjacent carbons on the second one. So same order, yes. Sorry, same order. Sorry, my chart. Different order, no. That's the answer to our question. Okay. Is the electronic organization different? No, because I don't have pi bonds, right? You have to have those things. I don't have them. Can I convert one into the other by rotating a sigma bond? No, right? That bromine right here is going back this bromine is coming forward. Because it's a ring, I cannot do that. If this was a straight chain, I could, but because it's a ring, I can't. I can get a conformation, or sorry, I can like put it in a chair conformation, right? But I can't rotate it all the way around. So can I convert one into the other by rotating a bond? No. Is the three-dimensional orientation different? Yes, right? This bromine is going back, this bromine is coming forward. So, sorry I scrolled so fast there. These guys are going to be stereoisomers of each other, right? The only way I can convert this first one into the second one is actually breaking this bond, right? Moving it from the back to the front and reattaching it to the same atom. Same atom again is important. If I attach it to a different atom, now I have constitutional isomers, right? Not stereoisomers. So I would play with the chart a little bit. Again, I've not made this before, so word of warning, you guys are my flow chart for relationship guinea pigs.